Welcome to Kinetics and Equilibrium, and here we go. So, excuse me, before we go any further, make sure you've got your reference tables. Shouldn't need a calculator for this unit, but you will need to draw upon some old stuff, some review, like this. How do you calculate energy transfer? We've got Q equals mc delta T. Where do you find that? That's on reference table T. One phase of matter, of course. Temperature change is T final minus T initial, and kinetic energy changes. And remember, so here we have our phase change diagram. So Q equals mc delta T is anywhere you see the line increase. Okay. The other formulas we have are Q equals MHF or Q equals MHV. So, excuse me, those are two phases of matter where potential energy changes, and there's no change in temperature or no change in kinetic energy. So this one, by the way, this is the solid to liquid. This is going to be heat of fusion formula. And this between liquid and gas is going to be the heat of vaporization. Those two flat lines. So I don't know that we have any calculations for that coming up, but that's some good review since we're going to be talking about phase equilibriums and that kind of stuff. So energy can either be taken in or given off, and hopefully you remember these words. Endothermic meaning heat is absorbed or taken in. If heat is absorbed, that's gross, sorry. If heat is absorbed, the surroundings are going to feel cold. So the ice cube is taking heat in from the air, from the table, okay? That's why it melts. The table is going to lose heat, and that's why it's going to feel colder. And exothermic is heat is given off from the system to the surroundings. So classic example, fire gives off heat to the marshmallow. Okay, so now there's something called enthalpy, and actually enthalpy has three different synonyms. It is the amount of heat in a system at constant pressure. We can also call it delta H, or more commonly, the heat of reaction. I would say that this and this are the two terms that we use most often in Regents chemistry. You will see this in higher level chemistries, but be prepared for either one of these. Delta meaning change. So when we're going to talk about it, this is going to be the change between the products and the reactants. Activation energy. Now, back in the old days, I don't even know if they do this anymore. When I bought my first cell phone, you had to get it activated. You couldn't just use it right out of the box. So you had to go to the store, pay extra money, actually, to get it started. You had to kind of kick-start it. And once it was activated at the store, you could use it. Now, I'm showing my age or my irrelevance in society. I don't know. I mean, the last time I got a new phone, maybe the store activated it. I don't know. I don't remember. I haven't got a new phone in a while. Anyways, activation means getting it started, kick-start it. So activation energy in a chemical reaction is the minimum energy that colliding particles must have in order to react. I like this one better. Energy to kick-start the reaction. Also, gotta love how they've just got to advertise all the time what I'm using. Anyways, activation energy starts it. The energy it takes to get it going, because everything requires energy. This strange thing is called a potential energy diagram. So in every potential energy diagram, you're going to see two flat lines and a curve in between. So you'll notice we have a flat line here, we have a curve upward, coming down, and flat lines again. This is an exothermic diagram. Without doing anything else, maybe you can already figure out why. What does exothermic mean? It means heat given off. And if heat is given off, you can see that we had heat starting here and then we end here. So this is why it's called exothermic. even though we're giving off heat, we still have this bump here, and we'll figure out why. All right, so this first line segment from the bottom of the graph, and by the way, I know there's nothing written on either axis, either axis, and that's okay. A lot of times this would be either energy or time. This would be energy too. So sometimes they call this the reaction coordinate. So this first arrow, there it is, represents the potential energy of the reactants. This shouldn't be energy. That was me misspeaking. So this would be energy over here. I guess I could write it. Energy. Hey, how would energy be measured? Probably kilojoules. Joules maybe, but they're kind of small. We'll just say time or reaction coordinate. So how much energy this reaction has to start? Because remember, we always have reactants going to products. So this is the reactant's potential energy. Now, you notice there are no numbers here. It's not quantitative, but if we wanted to know, we would just read the y-axis. Then, the distance between this flat line and the top of the hill, this crest, is called the activation energy, which we've just described. So you notice that it was a flat line. It was continuing, but it was flat, meaning our potential energy is going along. And then we gained enough energy to get something started until we reached this crest. The crest of the hill, the highest point in the whole graph, is called the potential energy of the activated complex. I like to think of this as a roller coaster. The activated complex is right at the top, and when you start going down, you know that kind of weird, I mean, if you're a roller coaster person, that kind of like unsettled, like, oh my gosh, my stomach, that feeling, that's the reaction's going to happen. Flat lines again. And so what does it mean when it flatlines again? That means our reaction is done. And so if the reaction is done, we have products. This is the potential energy of the products. Now, the last section is the difference between where you start and where you end. And you'll notice it doesn't matter how high this curve goes, right? As long as you start here and end here. So, can I get rid of that? Because that's now distracting. Okay. So now we call that last middle section, that is the delta H, also known as the heat of the reaction, also known as enthalpy, but be prepared for either one of those to be used more often. This is exothermic, okay? So exothermic means you start higher than you end because heat is given off. Exothermic graph. Now, if you were to calculate, remember we talked about how delta H is a change? Delta H is calculated by doing the potential energy of the products minus potential energy of the reactants. There is no set of numbers on the Y, and I get that. But if you look, let's just say smaller number minus bigger number, right? It's going to give us an overall negative value. So delta H for an exothermic reaction is going to be negative. We're actually going to need, coming up, reference table I. It's on page 5, so if you want to grab that. Okay, this is what we call an endothermic potential energy diagram. How do I know it's endothermic? Well, if you go back, you can see that. You start here, and then you end higher. We still have two flat lines, we still have a curve, but we're not going to go down as much because endothermic means heat is absorbed. Okay? So the regions of the graph are still the same. The first flat line, that's the PE of reactants. The amount of energy it takes to kickstart the reaction going from that flat line to the crest of the hill is called the activation energy. The utmost high peak, that's called the activated complex, the potential energy, PE, activated complex. So we're at the highest crest, and then we come down, excuse and then flat line again, meaning our reaction is over. So we are at the products. And the last section is the difference between where you start and where you end. And remember, that is called the delta H, or the heat of the reaction. Now, this is an endothermic graph. Let's talk about the sign of delta H, which again, I don't have any units here, so we can't be quantitative, but we can still figure it out. So delta H of an endothermic reaction, a bigger number, it's always PE of products minus PE of reactants. Bigger number minus smaller number. A bigger number minus a smaller number is going to still give us a positive overall value. So in an endothermic in an endothermic potential energy diagram, delta H will be positive. Okay. I don't think I don't have a slide for table I, but if you want to look there briefly, you'll see that delta H on table I, there's an asterisk next to it, where at the bottom it reminds you a minus sign indicates exothermic reactions. So any reaction on table I, I'll go back here. Oh, come on. So back to the exothermic, table I, you're going to see the negative delta H's. Any of those reactions would be exothermic. And then on this one, these would be table I, positive delta H's. Can you tell what that says? Sorry. That's the positive side. So, for example, I have table I, so something like hydrogen gas and iodine gas combining to form hydrogen iodide gas. It says positive 53.0 kilojoules. So that would be an endothermic reaction, meaning it's going to absorb energy from the surroundings. I've got a couple more definitions. The activated complex, which you remember is this top, the absolute crest of the hill. It is a very unstable arrangement of atoms that forms momentarily at the peak of the activation energy barrier, sometimes known as a transition state. So this is a lot of writing. The activated complex is not always on the regents. It's not super duper important. But you need to know that this is the maximum. This is the super unstable point before the reaction is undergoing. So my analogy, roller coasters can't stay very long at the top of the hill before they come down. Atoms can only remain unstable momentarily before the reaction continues. Same idea. And I think that's it for today. All right, take care.